Hello everyone, and welcome to this presentation. Today, we are going to learn how microstrip lines work and how to design a 50-ohm microstrip line for HFSS simulation. This introduction will give you all the theoretical background you need before starting the HFSS model. A microstrip line is one of the most common transmission lines in RF and microwave circuits. It consists of three main layers: a ground plane at the bottom, a dielectric substrate in the middle, and a metal strip on the top. This structure guides electromagnetic waves, and it is widely used in antennas, filters, couplers, matching networks, and RF PCB design. Here, we can see the structure more clearly. On the top, we have the copper strip that carries the signal. Underneath, we have the dielectric substrate, in our example, FR4, with a relative permittivity of 4.4. At the bottom, we have the ground plane. The width of the strip and the thickness of the substrate determine the characteristic impedance of the microstrip line. To design a microstrip line, we need to calculate two things: the effective permittivity and the characteristic impedance. The equation for the effective permittivity shows how the fields propagate partly in air and partly inside the substrate. Then, using the W/H ratio, we can compute the characteristic impedance. These formulas are used inside online microstrip calculators. In most RF systems, 50 ohms is the standard impedance. It minimizes reflections, allows maximum power transfer, and is compatible with common connectors like SMA. For this reason, when we design microstrip lines for simulators or RF circuits, we usually aim for 50 ohms. To calculate the width of a 50-ohm microstrip line, we need the substrate permittivity, the substrate thickness, and the target impedance. In our example, we use FR4 with epsilon r equals 4.4, a height of 1.6 millimeters, and a target impedance of 50 ohms. Instead of using the equations manually, we can use online microstrip calculators. We simply enter the substrate permittivity, the thickness, and the desired impedance. For FR4, with a 1.6 millimeter height and a 50 ohm target, the calculator gives a strip width of approximately 3 millimeters. With a width of about 3 millimeters, the microstrip line is well matched at 50 ohms. In simulation, we should expect S11 to be lower than -20 dB, which means excellent matching, and S21 close to 0 dB, meaning almost perfect transmission. This confirms that the line is correctly designed. Thank you for watching this introduction. In the next part, we will move to HFSS and build the microstrip line step by step. We will add materials, ports, the radiation box, run the simulation, and analyze the S parameters. Stay tuned for the practical HFSS demonstration.
Now, let's go to HFSS. In the HFSS design, we need three main elements: a ground plane, a substrate box, and a top metal strip, the microstrip line. First, we will insert a 2D rectangle to design the ground. We start from the origin and draw in the X and Y directions. This creates the ground plane. We can rename it here, change its color, and adjust the dimensions by clicking Create Rectangle. Since I started from the origin, the starting position is 0, 0, 0. I am using a rectangle of size 20 by 40 millimeters. So I set X size to 20 millimeters and Y size to 40 millimeters. Click this icon to fit the geometry into the viewing window. Now we need to design the substrate box. Click on Draw, Box. Again, since we want the box to match the ground size, we start at 0, 0, 0 and draw in the XY plane and in the Z direction. Rename the box as Substrate and assign the FR4 epoxy material. To change the material, click on Vacuum, Edit, and select FR4 Epoxy. Create the box. Since we started at 0, 0, 0, the substrate dimensions are X size equals 20 millimeters, Y size equals 40 millimeters, Z size equals 1.6 millimeters. Next, we will design the microstrip line on top of the substrate. Click on Rectangle and draw it on the top surface. Change its color if needed. Then click Create Rectangle to set the dimensions. Because the line must be centered on the substrate, the starting point is X equals 10 minus 1.5 millimeters, Y equals 0 millimeters, Z equals 1.6 millimeters. The line width is 3 millimeters, so X size is 3 millimeters, and I take Y size as 40 millimeters. This gives us the microstrip line on top of the substrate. This is our ground plane, our substrate, and our microstrip line. We can rotate the view to inspect them. We assigned the FR4 material to the substrate, but the ground and the line must be copper. Instead of assigning copper directly, we will assign them as perfect electric conductors. Select both planes, right-click, go to Assign Boundary, Perfect E. You can verify this under the Boundaries section. After assigning the boundaries, we will add the excitations. This is a two-port structure. Port 1 on one side and port 2 on the other side. To create the ports, we draw two rectangles in the XZ plane. Select the XZ plane, zoom in, and place a rectangle connecting the microstrip line to the ground. Rename it to port 1. Click Create Rectangle and enter the dimensions. Starting point is 8.5, 0, and 1.6 millimeters. X size equals 3 millimeters. The width of the microstrip line. Z size equals minus 1.6 millimeters. Assign the excitation. Right-click, Assign Excitation, Lumped Port. Make sure the impedance is 50 ohms. Select the two terminals, the upper trace and the ground, by clicking on the triangle markers. Finish the assignment. Similarly, create port 2 on the opposite side. Draw the rectangle. X size equals 3 millimeters, the width of the microstrip line. Z size equals minus 1.6 millimeters. Assign as a lumped port. Right-click, Assign Excitation, Lumped Port, and select the two terminals. Now, both ports are ready. Next, we design a radiation box around the structure. This box must be larger than the microstrip line. Click Draw Box, switch to the XY plane, and draw the box. Rename it, and assign the air material. Make the box transparent, so the internal structure remains visible. Set the box dimensions larger than the design. For example, X from minus 10 millimeters, Y from minus 10 millimeters, Z from minus 20 millimeters, X size equals 40 millimeters, Y size equals 60 millimeters, Z size equals 40 millimeters. Assign radiation boundary to this box. Right-click, Assign Boundary, Radiation. Now the structure is ready. We assigned boundaries, excitations, and radiation. Next, we add the analysis setup. Right-click Analysis, Add Solution Setup. Set the solution frequency to 5 GHz. Then, add a frequency sweep. Choose the fast type. Start at 1 GHz, stop at 20 GHz, step size 0.1 GHz. Validate the design, no errors, run the simulation. Once the simulation is complete, we create the results. Right-click Results, create Modal Solution Data Report Rectangular Plot. Select S parameters, choose S11, S21, S12, and S22. Choose the dB scale and click New Report. You will see. From the S parameters, we observe that S11 and S22 are both lower than -20 dB. This means that the microstrip line is very well matched at both ports, with almost no reflections. In other words, the input and output impedances are very close to 50 ohms. We also see that S21 and S12 are approximately 0 dB. This indicates that the signal is transmitted almost entirely from one port to the other with negligible loss. A 0 dB transmission level means that the line behaves nearly like an ideal, lossless transmission line. Overall, these results confirm that the 50-ohm microstrip line is correctly designed, well-matched, and provides excellent signal transmission across the frequency range. This is our final result. In the next video, we will design something new. Thank you for watching.